last day, I told you that when methane is formed by combination of 1 carbon and 4 hydrogen atoms, so carbon is 1s2, 2s2, 2s1, 2px1, 2py1, 2pz1 in excited state. Okay, so when it is combining with 4 hydrogen atoms, the 4 sigma bonds that will be formed, will they be alike or they will be different? Yes, tell me, will they be alike or will they be different? This is the excited state electronic configuration of carbon, and these are the 4 hydrogen atoms. So when they combine with each other, will they be of same type of sigma bond or different type of sigma bonds?
They're different.
One of them is different because it will be formed as a result of SS overlap, isn't it? And rest
Yes,
of
sir.
them should be similar because they are formed as a result of SP overlap. So accordingly, if this is the case, out of the 4 sigma bonds, one of the bonds should be shorter, isn't it?
Yes, sir.
Yes.
And rest 3 should be equal. And Px, Py, Pz are mutually perpendicular to each other. And if they are mutually perpendicular to each other, what should be the bond angle between the 3 such bonds?
90 degree.
90 degree. But the reality is something else. What is the reality? When methane is produced, all the carbon hydrogen bond lengths are equal. And not only are they equal, the bond angles are also equal and they are 109 degree 28 minutes. So if you consider the simple valence bond theory, you cannot explain the actual shape of methane, because if you go by simple valence bond theory, 3 of the carbon hydrogen bonds, any 3 of them must be equal, the 4th one must be different. But what is the reality? The reality is all 4 are of same bond length and none of the bond angles are 90 degree. Rather, what is the bond angle? Tell me.
109 degree.
28 minutes. So
28.
methane is one such example which could not be explained on the basis of simple valence bond theory, and that is why it was suggested that actually carbon does not combine with hydrogen in the excited state. Prior to combining, the valence shell orbitals intermix among themselves, and this intermixing of orbitals is referred to as hybridization. Do you remember now?
Yes, sir.
Okay.
Yes.
So hybridization is intermixing of orbitals to give new orbitals, all of which have same size, shape, and similar energy. So write down the topic, hybridization, a very, very important concept in chemistry. Hybridization. This concept was put forward by Pauling, P-A-U-L-I-N-G, Pauling. According to him, atomic orbitals mix together to generate a new set of equivalent orbitals called the hybrid orbitals. Called the hybrid orbitals. These orbitals are actually used in bond formation. These orbitals are actually used in bond formation. Then only you can explain why all the bond lengths are found to be exactly equal. This concept is called hybridization. So this whole concept of formation of hybrid orbitals by intermixing of pure orbitals is referred to as hybridization. Okay, have you written down?
Yes, sir.
Yes, sir.
Okay. Now we'll talk about some important features of hybridization, which we call as the salient features. So we need to understand certain points. So move on to the next subtopic, salient features of hybridization. Salient features of hybridization, which means that some important points need to be remembered when we talk about hybridization. Point number one, the number of hybrid orbitals produced is equal to the number of pure orbitals involved in hybridization. So last class also I told you that when hybridization occurs, how many hybrid orbitals will be produced depends upon how many parent orbitals or pure orbitals are involved in intermixing. If it is sp3, which means that 1s and all the 3p are involved, then total of how many hybrid orbitals will be produced?
4.
4. If it is sp2, that means 1s and 2 of the p's are involved, then the number of hybrid orbitals produced will be 3. So likewise, depending upon how many parent orbitals are involved in hybridization, accordingly that many hybrid orbitals will be produced. Point number 2, The hybrid orbitals produced are always equivalent in shape and energy. Okay, so the new hybrid orbitals produced due to intermixing will always be having same energy and same shape. Point number 3. The hybrid orbitals are more effective in forming stable bonds than pure orbitals. So hybrid orbitals have a greater capacity of forming stable bonds as compared to the pure orbitals. Point number 4. These hybrid orbitals arrange themselves in three-dimensional space so as to have minimum repulsion and maximum stability. So after the hybrid orbitals are produced, they try to acquire such a position in three-dimensional space so that the repulsion is minimum between them, because lesser the repulsion, more stable will be the structure. So I hope all the 4 points are clear. If you have got any doubt regarding any of the points, you can clear it out.
Sir, number 3.
Number 3, when a bond is formed between pure S and pure P, and when a bond is formed between hybrid orbitals, then the hybrid orbitals are found to form stronger bonds as compared to pure S or pure P orbitals.
Okay, sir.
Tell me after you have completed writing the points.
Yes, sir. Done.
Done? All of you have written?
Sir, no,
Yes,
sir.
sir.
Last point is
Okay,
not
write
done.
it down.
Sir, please
Yes.
explain the point.
Which point?
Last point, number 4.
Last point. Suppose there are 4 hybrid orbitals produced in sp3, when one S and all the 3 p orbitals are involved. So total hybrid orbitals produced will be how many? 4, isn't it? So out of all the geometrical figures, if 4 hybrid orbitals want to arrange themselves in space, then it is found that the tetrahedral shape is the most suitable shape, because in that shape, the repulsion between the hybrid orbitals will be minimum, because ultimately hybrid orbitals are also electron clouds as they are formed of electrons. So they will have repulsion in between. Now, more the repulsion, lesser will be the stability, and nobody wants to be less stable, and that is why they try to acquire such a shape so as to have minimum repulsion and maximum stability. So if there are 4 hybrid orbitals, then which shape is best suited so as to have minimum repulsion and maximum stability? It is tetrahedral shape. If suppose 3 hybrid orbitals are produced, then which is the best shape so as to have minimum repulsion and maximum stability? It will be trigonal shape. What is trigonal shape? Trigonal shape means when the bond angle between the 3 is 120 degrees. Understand?
Yes, sir.
Can you tell me what will be the shape acquired by hybrid orbitals if they are 2 in number?
Mm,
So linear.
Linear. Okay, so as to have minimum repulsion. It is similar to that of VSEPR theory shapes that we got. If there are 4 hybrid orbitals, the shape will be tetrahedral. If there are 3, it will be trigonal planar. If there are 2, it will be linear. If it is 5, it will be trigonal bipyramidal. So same shapes that we discussed during the VSEPR theory under regular shapes. Understood?
Yes, sir.
Okay.
Sir, the shape can be referred from this table, no? Sir, that you gave us.
Yeah, you can consult that table also, VSEPR theory table, only for regular structures. Okay.
Okay, sir.
So after that, we talk about, see, we need to understand each and every point very clearly. And it's good that you asked me if it is not clear. Important conditions for hybridization. Important conditions for hybridization. So first important condition is only valence shell, outermost shell, orbitals of an atom are involved in hybridization. Inner shells are not. Only valence shell orbitals are involved in hybridization. So inner shells have no role to play in hybridization. The orbitals involved in hybridization should have comparable energies, which means that suppose S is overlapping with P orbitals, so both the S and P should have more or less comparable energies. When I use the term comparable energies, it means that there should not be large difference in the energies between the S and P orbitals. There should be slight difference. And that is what has been said, that those orbitals which are involved in hybridization must have comparable, or we can say similar energies, even if not equal energies, but similar energies. Promotion of electrons. So last class we have discussed, to explain the tetravalency of carbon, beryllium and boron, that one of the electrons get excited, then only we can explain the tetravalency of carbon, trivalency of boron and divalency of beryllium. But promotion of electron or excitation of electron is not essential for hybridization. What does that mean? It is not necessary that before undergoing hybridization, there should be excitation of electron. We will come across some examples where even if there is no excitation going on, still hybridization occurs. Point number 4. It is the orbitals that take part in hybridization and not the electrons present in them. In some cases, even filled orbitals of valence shell may take part in hybridization. So it has nothing to do with the fact that only half-filled orbitals can only take part in hybridization. It is not the electrons that are taking part in hybridization. It is actually the orbitals which are taking part in hybridization, which means that even if the orbital is fully filled, that also can take part in hybridization. So it is always the central atoms, the valence shell orbitals of central atom, that take part in hybridization, and after they hybridize and form required number of new hybrid orbitals, depending upon whether those hybrid orbitals are half filled or completely filled, accordingly that many side atoms will be invited, and you will get to understand this topic when we gradually come across the examples. But for the time being, you simply remember all these points, and after we get the examples, you should be able to correlate with that of what points have been stated.
Okay, sir.
Now, if you are given a molecule and you are asked that the central atom shows what kind of hybridization, so there are two ways of calculating. One way, I think we discussed last class, that you have to add up the valence electrons, and if the total number of valence electrons comes out to be 8 or less, you have to divide it by 2, and if it is greater than 8, you have to divide it by 8. So likewise, we can calculate the hybridization. So that method of predicting the hybridization I'll be giving you now. Have you written down all the points? Can I proceed?
Yes, sir.
Yes, sir.
Yes, sir.
So then write prediction of the hybridization of central atom. So at first we will talk about for inorganic molecules or ions. Inorganic molecules or ions. Because for organic or carbon compound, or hydrocarbons, relatively it is simple, but for inorganic molecules or ions, we need to follow one formula, a simplest formula with the help of which you can quickly calculate the hybridization. The first thing that you need to do is add up all the valence electrons, just as we used to do in Lewis dot structure. Add up all the valence electrons, and accordingly we will categorize into two types. So let us say that the valence electrons V, okay, if it is less than or equal to 8, divide V by 2, and we know that if you divide any number by 2, the remainder will be either 0 or 1. So whatever questions you are getting, add it up with the remainder if remainder is there, otherwise only question. And let us say that the answer comes out to be X. So let us keep this answer intact. Now what if V is greater than 8? Okay, so the left hand side was for less than or equal to 8. Right hand side will be greater than 8. If it is greater than 8, divide the number by 8. Now when you divide it by 8 and the remainder comes out to be greater than 1, if it is less than 1, stop it there, and as usual add up question plus remainder. But if the remainder comes out to be greater than 1, further divide the remainder by 2 if it is greater than 1. So because you are dividing it 2 times, so you will get 2 questions. So add question 1 plus question 2 plus remainder if any, and let us say this is also X. So it is like saying that suppose the number comes out to be 34. When you divide it by 8, 8 fours are 32. Remainder comes out to be 2, okay, which is of course greater than 1. So further divide this number by 2. Are you getting my point?
Yes, sir.
So since the first remainder comes out to be greater than 1, you further divide it by 2. Now this is question 1, this is question 2, this is remainder. So remainder is 0. So you have to simply add up 4 plus 1, that comes out to be 5. So this way from both sides we are getting some X. So what value of X you are going to get? Based upon that, now we are going to decide the hybridization. The first you write down this flow chart, and thereafter I will give you the conclusion of the results that will be obtained. Done? Can I proceed? Yes.
Yes, sir.
Yes, sir.
Okay. So now we have X from both the sides. So suppose I make two columns, value of X and hybridization. So if X comes out to be 2, then the type of hybridization will be sp, because two orbitals are involved. If it is 3, it is sp2. If it is 4, it is sp3. If it is 5, it is sp3d. If it is 6, it is sp3d2. If it is 7, it is sp3d3. So the numbers that you are getting as result is same as that of the orbitals involved in hybridization. So depending upon how many hybrid orbitals are produced, you are getting that number. So in sp, as there will be two hybrid orbitals produced, the X value is 2, sp2 3, sp3 4, that way. Is the method clear?
Yes, sir.
Yes, sir.
Okay. Now coming to the second part, which is relatively simple. For organic molecules. Now, the central atom in organic molecules is carbon. So carbon can show either sp, sp2 or sp3. They cannot show the hybridization involving d orbitals. Why? Because carbon belongs to the second period, and second period elements do not have d orbitals in them, because of which carbon can show only sp, sp2 and sp3. So as I said, it is relatively much simple that if a carbon is surrounded by only sigma bonds, then this carbon will be sp3. If carbon is associated with double bond, it is sp2. And if carbon is associated with triple bond, it is sp. As simple as that. So suppose you have an organic molecule with too many carbons present in it, and say this is the molecule. And if you are asked to calculate hybridization of each and every carbon, so just see that carbon atoms are associated with double bond, triple bond, or only single bond. So what do you think will be the hybridization of the first carbon accordingly?
sp2.
So you see a double bond associated with it, it is sp2. Similarly, this is also sp2, because this is also associated with double bond on the left hand side. What about this carbon?
sp3.
sp3, very good. What about this carbon?
sp.
sp. What about this carbon?
sp.
sp again. See, all of you have understood this or not? So doubly bonded carbons are sp2, triply bonded carbon are sp3, and singly bonded carbon are sp3. Triply bonded is sp. I hope it is clear for organic molecules.
Yes, sir.
Okay. Boys, is it understood?
Yes, sir.
Oh. So now, for organic molecules, I have already given the example. Let us try out some inorganic molecules or ions. So write down the question. Predict the hybridization of the central atom in the following. So let us start away with an ion, sulfate ion, SO4 2 minus. So SO4 2 minus, valence electron of sulfur is 6. Each oxygen is also 6, and because it is an ion with 2 extra electrons, to add up 2 extra electrons to it. So upon adding the valence electrons, it comes out to be 32, isn't it?
Yes, sir.
Okay. Now this number 32 should be divided with what?
8.
8, of course, it is greater than 8. So when you divide it by 8, you don't get any remainder. So directly the question 4 is the answer, and 4 stands for which hybridization?
SP3.
SP3.
sp3. Clear?
Yes, sir.
Try out for carbon dioxide quickly and tell me.
Sir, SP.
sp, okay. Anyone stuck in any of them? You please tell me. I'm writing down the results. See whether you are getting or not. Don't write the result directly. I just want you to find out first and then see whether you are going correct or not.
Yes, sir, done.
So let us wait for others. Fahim, getting it?
Yes, sir, got it.
Trishna? Trisha.
All sulfur issue.
Okay. Tanishka is there?
Yes, sir, done.
Done? Getting it?
Yes, sir.
Abhilash?
Yes, sir.
Getting all them?
Yes, sir.
Okay. So let me give you more, because as such, you're going fast. PO4 3 minus, XCF2, XCF4, SnCl2, BrF5. Try them quickly. If you are not aware of valence electrons for anyone, you can ask me, I'll help you out.
Sir, for SN.
SN belongs to carbon family.
Sir, for XC.
For XT,
Xc is a noble gas. How many electrons will you give for noble gas in the valence shell?
8.
8.
8. Yes. I'm writing down the answers. I hope the answer matches with what you are getting. So in NH4 plus, just now given, you have to subtract 1 electron from the total valence electrons. Any answer which you are not getting, please tell me. I'll show you. Tanishka, getting all of them?
Yes, sir.
Balaji,
Yes, sir.
got all of them?
Yes, sir.
Okay. Any doubts in any of them? Can I proceed? Yes.
Yes, sir.
Yes, sir.
Okay, fine. So now we know how to find out in advance the hybridization of the central atom. And you can expect questions on this. A very important topic. So it's a shortcut formula. Now we go to discuss in details about the molecules and hybridizations in particular. So write the topic as types of hybridization. Types of hybridization. So under types of hybridization, we'll first talk about sp3 hybridization. So as the name implies, in this type of hybridization, 1s and all the 3p are involved in hybridization. The type of hybridization in which 1s and all the 3 p orbitals are involved in intermixing to produce a total of 4 sp3 hybrid orbitals is called sp3 hybridization. So in this type of hybridization, eta s mane ki, it can be 2s also, it can be 3s also, 4s also, jikono s will combine with the 3p orbitals belonging to the same valence shell to produce a total of 4 sp3 hybrid orbitals. And this I can show with the help of this diagram. You know that S is spherically symmetrical and all the 3p orbitals will be intermixing with S, producing a total of 4 hybrid orbitals. These hybrid orbitals are shown in such a way that it has got both S characteristic as well as P characteristic. So these are sp3 hybrid orbitals. They are 4 in number, and characteristic of sp3 is such that the S character is 1/4, because total of 4 hybrid orbitals, total of 4 pure orbitals were involved, one of which is S. So therefore, the S character is 25% and P character is 75%. So 25% S and 75% P character. So just now, as we have stated, that when 4 hybrid orbitals are produced, what is the best geometrical shape they will acquire so as to have minimum repulsion and maximum stability?
Tetrahedral.
Tetrahedral. So these 4 hybrid orbitals arrange themselves tetrahedrally so as to have minimum repulsion and maximum stability. So they are going to arrange themselves tetrahedrally so as to have minimum repulsion and maximum stability. And that is why the shape acquired is tetrahedral. Any doubt up to this much? Please ask me. So accordingly, the shape that will be acquired by these 4 hybrid orbitals, as I said, is tetrahedral. And in order to be tetrahedral, this is the shape acquired: 1, 2, 3, and 4. So any atom which undergoes sp3 hybridization will acquire this shape. I cannot put in any electron in these orbitals because I have not mentioned any atom. So when we mention the atom, it will be more clear to us that what will be the electrons present in them. हो गया? Can I rub it?
Yes, sir.
All of you have written?
Yes, sir.
Yes, sir.
Okay. So now we will talk about some common examples, and thereafter we will discuss the shapes of such molecules. But the main thing is, no matter whatever be the central atom, if it undergoes sp3, it will try to acquire tetrahedral shape. Examples include methane, ammonia, water, all alkanes, etc. So these are the molecules. With the help of the formula, you can calculate that the central atom will show sp3 hybridization in all of them. So let us first of all talk about shape of methane molecule under sp3. Who is the central atom in methane?
C.
C.
Carbon. Okay, so whosoever is the central atom, we will draw the energy diagram of that central atom. 1s, 2s, 2p. Carbon, as we know, in the ground state has electronic configuration of 1s2, 2s2, 2p2. Okay, so rather than writing horizontally, I am writing it vertically from bottom to top. The energy is increasing. But will carbon combine in its ground state with the 4 hydrogen atoms?
No, sir.
No, sir.
How many unpaired electrons do you find in the ground state?
2.
2. But how many hydrogen atoms carbon is inviting?
4.
4.
4. It means that it will undergo excitation when one of the electron from 2s will jump to 2p, making a total of 4 unpaired electrons. So tetravalency of carbon can be explained because now it has 4 unpaired electrons. But still, it is not going to invite the hydrogen. Otherwise, the same controversy arises that one bond should be shorter as compared to the other 3 bonds. And therefore, it is suggested that prior to inviting the hydrogen atoms, this s orbital will overlap or intermix with all the 3p orbitals in hybridized state. GS stands for ground state, ES stands for excited state, HS stands for hybridized state. Now, if this orbital intermixes with all the 3p orbitals, how many hybrid orbitals will be produced?
4.
4. And the energy of these hybrid orbitals will be lying in between this and this. So let me show the hybrid orbitals with the help of circle. So after the hybrid orbitals are produced, whatsoever be the number of electrons that were present initially in the pure orbitals, they will be distributed following the Hund's rule. So total of how many electrons were there in the pure orbitals involved in hybridization?
4.
How many electrons? 4. So these 4 electrons are to be distributed equally in these 4 hybrid orbitals. So this is sp3 hybrid orbitals. So we see that as there are 4 sp3 hybrid orbitals, so of course the shape acquired by the central atom should be tetrahedral. And all of them will have 1 unpaired electron each. And these unpaired electrons present is going to decide that how many hydrogen atoms should be invited. So as the number of unpaired electrons are 4, so there will be 4 hydrogen atoms that will be invited, and every hydrogen atom has 1 unpaired electron. They will be coming from 4 different directions, producing a total of 4 carbon hydrogen bonds which are exactly of same length, making a bond angle of 109 degree 28 minutes. What is the nature of this bond? Of course, S is involved, so it will always be sigma. But what are the orbitals involved? This orbital is sp3, this orbital is s, so therefore it is sp3s sigma bond. All are sp3s sigma bonds. So total of 4 sp3s sigma bonds are produced. See whether it is understood or not.
Yes, sir. What are the 3 ball-like structures you drew in the center?
These are not ball-like structures. You remember I have drawn hybrid orbital having this particular shape. Hybrid orbitals of
Yes, sir.
this one, na?
Yeah, yes, sir.
When they will be combining, so this small ball shape will be coming in between.
Okay, sir.
The larger ones will be facing outwards and smaller ones will be facing inwards to have greater overlapping. Why is the carbon inviting 4 hydrogen atoms only, not 3 or 2? Yes, can anyone tell me? Why 4 hydrogen atoms? Because carbon has how many unpaired electrons in the hybridized state? 4 unpaired, na?
Yes, sir.
So to fulfill, to complete, to pair up the electrons, so it will be inviting 4 hydrogen atoms only. Understood?
Yes, sir.
Yes, sir.
So are not the 4 carbon hydrogen bond lengths exactly equal in length? Are they equal in length or not?
Yes, sir.
Because all of them are
Yes, sir.
sp3s.
Yes,
So
sir.
if carbon would have directly bonded with hydrogen atom without undergoing hybridization, then one bond length should have been shorter and 3 of them would have been relatively longer and equal. But the reality shows something else. It says that all 4 bond lengths are equal, which means that prior to inviting the hydrogen atoms in excited state, the valence shell orbitals of carbon undergo hybridization, producing 4 hybrid orbitals, which all have same size, shape, and energy. And once they are produced, then only the hydrogen atoms will be invited. Understood?
Yes, sir.
Can I move on?
Okay, sir.
Now let us try out the second example. The second example in the list is ammonia. Who is the central atom of ammonia?
Nitrogen.
Nitrogen.
Nitrogen. So we need to now discuss the energy diagram for nitrogen, which is 1s2, 2s2, 2p3. So as you can see in the ground state itself, nitrogen has the same valency as that of the demand of the molecule. So there is no need of any excitation, isn't it?
Yes, sir.
Yes, sir.
So there will be no excited state for nitrogen. And this is what is one of the points saying that promotion of electron is not the mandatory criteria. So nitrogen has already 3 unpaired electrons in its valence shell, and therefore there is no point of exciting it. So the nitrogen also undergoes sp3. From the formula we can calculate, and this is going to again overlap with these 3 orbitals, forming a total of 4 hybrid orbitals only. But the number of electrons now are not 4. How many electrons are totally present in the combining atoms, combining orbitals?
3.
3.
1, 2, 3, 4, 5. This is also involved, na?
Yes, sir.
So total of how many are involved electrons?
5.
5. Is it understood? This S intermixes with all the 3p. So গোটেই কেইটা electron count কৰিব লাগিব নহয় জানো?
Sir.
So total of 5 electrons are to be distributed in 4 hybrid orbitals. See whether it is clear or not. Is it understood or there is some confusion? Clear out your confusion if any. In carbon, you had 4 electrons in the valence shell, but in nitrogen, how many electrons do you have in valence shell? 4 or 5?
5.
5. So these 5 are to be distributed in 4 hybrid orbitals. Hybrid orbitals to 4a form hobo because it is sp3, which means that out of the 4 hybrid orbitals produced, how many hybrid orbitals have unpaired electrons?
3.
3.
3. And one of them is completely filled up or not?
Yes, sir.
Yes, sir.
So how many hydrogens will be invited now?
3.
3.
3 only. So it will come here, it will come here, it will come here. And what was supposed to be tetrahedral is now pyramidal, because this is not going to determine the shape, isn't it?
Yes, sir.
Yes, sir.
So nitrogen has 1 lone pair and 3 bond pairs with hydrogen. If all of them would have been bonded pair, the shape would have been regular tetrahedral shape. But this is not regular tetrahedral shape, rather it is pyramidal shape. And bond angle will also decrease. In VSEPR theory, we have discussed that due to the presence of lone pair, the repulsion will be experienced by the bonded pairs. They will come closer and bond angle will be lesser than 109 degree 28 minutes. Understood?
Yes, sir.
Yes, sir.
Complete it. Then we will move on to water. Tell me after you have completed so that I can go to the water molecule. Here also the three bond lengths, I mean the bonds that are formed are sp3s only. All three are sp3s because overlapping is between sp3 hybrid orbital and pure s orbital of hydrogen atom.
Yes, sir. Done.
Okay, now we move on to water. Who is the central atom of water?
Hydrogen.
No.
Oxygen.
Though we write H2O, the central atom has to be one, na?
Yes, sir.
So hydrogen is not the central atom, oxygen is the central atom. What is the electronic configuration of oxygen? It is 1s2, 2s2, 2p4. So one more electron increases. So how many electrons will be distributed after 4 hybrid orbitals are produced?
6.
6, which means one more hybrid orbital will be paired up or not?
Yes, sir.
The water was also supposed to be tetrahedral, but how many hydrogens will be invited now by oxygen?
2.
Only 2, because 2 of the hybrid orbitals is completely filled up. These 2 have unpaired electrons. So accordingly, only 2 hydrogen atoms will be invited. Understood or not?
Yes, sir.
And what was supposed to be tetrahedral now comes out to be inverted V shape. So oxygen has 2 lone pairs and 2 bonded pairs, and bond angle further decreases as there are 2 lone pairs. Clear?
Yes.
So what is common between carbon, nitrogen and oxygen in methane, ammonia and water?
Hydrogen.
No, that is not common. That means in context of hybridization, tell me what is the common
sp3s.
between, they all are sp3 hybridized, isn't it?
Yes,
Yes, sir.
sir.
The carbon is also sp3 hybridized, nitrogen is also sp3 hybridized, oxygen is also sp3 hybridized. Then what makes the difference in the shapes? The number of unpaired electrons in the hybrid orbitals, isn't it?
Yes, sir.
So in carbon, all 4 hybrid orbitals have one unpaired electron each. Therefore, it was inviting 4 hydrogen atoms. In ammonia, 3 unpaired electrons were there, so 3 hydrogens. In water, 2 unpaired electrons, so 2 hydrogens. Clear?
Yes, sir.
Shubhayu, is it understood?
Yes, sir.
So all the 3 central atoms discussed so far are sp3 hybridized. So what was the expected shape all should have acquired?
Tetrahedron?
Tetrahedral. But are they acquiring tetrahedral?
No, sir.
No. Why? Because the number of unpaired electrons are different, isn't it?
Yes, sir.
Yes, sir.
So if I tell you that the carbon which undergoes sp3 hybridization will have this, nitrogen undergoing sp3 hybridization will have this, and oxygen undergoing sp3 hybridization will have this shape, will I be wrong? See, are you getting the difference? This is carbon, this is nitrogen, and this is oxygen, isn't it?
Yes, sir.
Yes, sir.
So all are undergoing sp3 hybridization. That is why 4 hybrid orbitals are produced. But what makes the difference in them? The distribution of electrons, because atomic number of every atom is different. For carbon, there are 4 unpaired electrons in the valence shell. For nitrogen, there are 5. For oxygen, there are 6. So therefore, the number of hydrogen atoms invited will also be different. Whereas in case of carbon, all 4 will be inviting hydrogen, isn't it?
Yes, sir.
Yes, sir.
In case of nitrogen, only 3 will be inviting. In case of oxygen, only 2 will be invited. Understood?
Yes, sir.
Yes, sir.
Now, keeping in mind this fact that carbon has 4 unpaired electrons in it in sp3 hybridized state, if you are to draw the shape of the second member of the alkane family, methane is the first member with 1 carbon atom at the center. But if you are to draw the shape of ethane, how many center are there in ethane? Tell me.
2.
2. It is a dicentric molecule and both the carbon atoms are the centers. And just now I have told you that if carbon is sp3 hybridized, it will have this configuration, isn't it?
Yes, sir.
And how many such carbons are there, both of which are sp3 hybridized?
2.
2 carbons are there. So if you need to explain the structure of ethane on the basis of hybridization, what we will do is we will combine one of the sp3 hybrid orbitals of one carbon with one of the sp3 hybrid orbital of another carbon by making it to move in downward direction. Understood?
Yes, sir.
Etu moi ghurai dim tolole so that the other one also can overlap. So what type of sigma bond is formed between the 2 carbon atoms? What is this lobe? Is it not sp3? What is this lobe? This is also sp3. So what type of sigma bond will this be?
sp3, sp3.
Very good. sp3, sp3. আচ্ছা বাকি যে এই ছটা থাকি গল, what will they do?
Combine with hydrogen.
Total of how many hydrogens will be invited now?
6.
বুঝি পাইছা নে?
Oh, sir.
Yes, sir.
So this is shape of ethane. What is the difference between ethane and the previous 3 molecules?
Their center atom was 1 here, 2.
Very good. So in ethane, you have 2 centers, but in methane, ammonia and water, you had only 1 center. So in ethane, both carbons are sp3 hybridized. Ethane, mind you, is an organic molecule. And I have already told you that if carbon atom in organic molecule is surrounded by only single bonds, the carbon atoms will be sp3 hybridized. So total of how many sigma bonds do you find in ethane? Keta sigma bond আছে total ইথেনত এই structure to চাই কোৱাচোন
7.
7. Are all the 7 sigma bonds are of same type?
No, sir.
How can you further categorize it into?
sp3, sp3 and sp3, sp.
sp3 sp3 কোন কেটাৰ মাজত ফৰ্ম হৈছে কাৰ্বন আৰু কাৰ্বনৰ মাজত নহয় জানো
Oh,
Oh,
sir.
sir.
তো কাৰ্বন কাৰ্বন will form sp3 sp3 আৰু ছটা কাৰ্বন হাইড্ৰোজেন will form sp3s.
Yes,
Am
sir.
I clear?
Yes, sir.
The total of 7 sigma bonds are formed, but 2 types. Carbon carbon is sp3 sp3 and carbon hydrogen 6 in number are sp3s. Understood?
Yes, sir.
Yes, sir.
Okay. So ekhini bhalke ebar sai loba and next day we'll discuss about sp2 hybridization. But for that sp3 should be very much clear to you. Please go through them once. So next day we will discuss the sp2 and sp hybridization. Thank you. Good night all of you.
Thank you, sir.
Thank you, sir.